Hi, I'm Reynaldo Lima, and I will be presenting modeling and simulation of a small-sized robot kicking mechanism. This work was developed with Daniela, Vacarini, Faria, Luiz, Góes, and Maximo. As an introduction, small-sized league is a category within RoboCup competition, a worldwide robot soccer event aiming in AI, artificial intelligence, development. The small-sized league robots are omnidirectional and wheeled robots, and they use low and high kicking mechanisms to pass between robots or to shoot to the goal. The rules are similar to regular soccer. The difference is that they use robots. This work focuses on the kicking mechanisms. The strategy for the kick is to release energy that is stored within a device. The energy stored may come from different sources or in different types. Common approaches are pneumatic, elastic, and electrical systems. The solution used is an electrical solenoid with a moving plunger inside of it that is made of ferromagnetic material, and thus the plunger is driven forward until it collides with the ball and completes a kick. The mechanism provides a better control over the final ball speed when compared to the other options. As in soccer, it is important that we have different options of kicks to differentiate from pass to shoot. This is the best approach and the one that we study on this work. Running through a bibliographical review, Maximo et al. Developed the model considering the solenoid current to be constant, which is an approximation. Zolavandri et al., on the other hand, consider the current model to be linear with time, that is again an approximation. Aliali et al. Had a different approach. It did not focus on the circuit, but rather on the magnetic field of a solenoid. Finally, De Marchi et al. Provides a similar approach as we do, with a computational result considering a variational current, but it stumbles on the discontinuity that they do not explore. Our model studied the solenoid as two subsystems, a resistance capacitor inductance circuit and a mass spring damper mechanical system. Starting with the electrical model, we have a capacitor of capacitance C, charged with a high voltage, around 150 volts, which is way higher than the battery that we have that has 11 volts. We have a dedicated board booster to turn those 11 volts to 150 and to charge this capacitor. Besides that, we have a resistor R and an inductance L, that is our solenoid. When the kick is actioned, the circuit closes and it becomes what is seen in the figure, and the equations of the model are described as follows. Although the model described seems effortlessly simple, with only two equations, the inductance function is complex. In this work, we developed the expression for the inductance as a function of the displacement of the moving plunger. We chose to express it as such to make it easier to connect with the mechanical system. This model could result in a discontinuity from the high value of inductance that it happens when the plunger is completely inside the solenoid for a rather small instant of time. This happens as, for most approaches, we consider the plunger to have the same side of the solenoid. In this work, we avoided the problem by considering the solenoid to have greater length than the plunger itself. Thus, there is a moment of constant inductance that lasts from the time the plunger is with x equals to L0, that is the plunger's length, to the solenoid's length that in the model is represented by D. We now have the final electrical circuit equations, in which we chose to represent current function and the rate of the current with relation to the time, as we would track those measures. Proceeding to the mechanical system, we have a simple mass spring damper model, with a magnetic force driving the movement. Derive the force expression from the magnetic energy that rises from the current, where we represent it as a function of the flux linkage lambda, which is common for the magnetic energy analysis. We follow the approach of Carnot and Fitzgerald textbooks. It is shown there the expression of the force, and knowing the magnetic force, the system can be described as follows. K is the elastic constant, B is the damper constant, M is the plunger's mass, and Fc is the Columbian friction that we add to the model to better represent the metal-on-metal contact that the plunger has within its assembly. Now we have the complete system of equations, and it may continue to the simulation itself. Here we recover those 4 equations of our model, 2 from the electrical system, 2 from the mechanical system, and here below we show the MATLAB variables that we used to represent each of those. As the current is I, the current rate of change is IP, the speed of the plunger is V, and the rate of change, the acceleration of the plunger, is Vp. Here you see the block diagrams of the model with the cited variables, in addition to other variables as Q, that is the capacitor charge and related to the current, and X, that is plunger's displacement. The integrations presented in the model are represented in the block diagrams by the fractions 1 over S, and finally the main part of the program is inside a MATLAB custom function that we feed those 4 equations from this slide into this block here, and we iterate within time. The main variables that we observe are the time of the circuit, the time the circuit is running, and the speed that we have as an output. The values used for the simulation are presented here in this table, and for the results we have here, we're tracking, as said, the time in the x-axis. The time we present there is the time that the circuit is working, that meaning from the time the circuit is closed to the time the circuit is open again. And the output, the epsilon axis, we have the speed of the plunger. The black line is prediction of the movement by the simulation, and we have recovered 3 experimental points known for being our robot's standard options. It is important to notice that the model provides the plunger's speed, and our experiments focused on recovering the ball's speed. To compare it, we suppose the total momentum transference between the two, and we got those ball's speed and transformed those into plunger speed. As you can see, the model is promising, with the team planning on mapping more experimental points to further validate the model. Nonetheless, the model already hints us into directions for a robot's kicking mechanism project. Finally, we reinforce the contributions of our work that provides a computational solution that considers the discontinuity of the model while providing a more accurate approximation of the real system and when compared to the literature provided. As for future work, the team plans on mapping a wider range of experimental data in order to validate and improve the model. Furthermore, some improvements into the theoretical model can yet be implemented, as considering the time from which we turn off the circuit into the actual plunger collision with the ball, as those events may not occur at the same time as we consider, and this difference in time could result in slowing the plunger until it reaches the ball. As for the reference that we used, are presented here, and we finish the presentation of the work. Thank you.